Awesome. Okay, so this is speech synthesis from ECoG using densely connected 3D convolutional neural nets. It came out in 2019. This paper is structured a different, oh, okay, here, this is like the actual starting, right? So yeah, published mid 2019. So this is like early mid 2019. So this is about 2 years old now, but I think it's still kind of a breakthrough paper. I remember there was like a lot of like press coverage when it came out. I'm not sure press coverage, but I mean like there was a lot of noise about it in the neurotech community when it came out. Basically, um, let's just break down what this title means. Speech synthesis, right? So generating speech, right? Like auditory signals um, of like a human speaking from ECoG. This is electrocorticogram. So it's an invasive technology. Basically, you stick these electrodes into the cortex of the human brain, or on the surface of the cortex of the human brain. Right, the cortex is just the top few millimeters of your brain where most of the actual computation takes place. Right, like the gray matter versus the white matter that's like inside. Um, so that's what an ECoG is, right? Measuring those neuron signals in the cortex of your brain using densely connected 3D convolutional neural nets. Um, so this is basically just like specifying the type of neural net it is. A neural network is a machine learning algorithm, right, that learns to predict certain things. A 3D, so okay, let's go one by one. A convolution, so everyone understand what a neural net is? I guess most of you have like a vague understanding, right? Basically, you have a ton of neurons, right? Input neurons, and then there's like layers of neurons where each one feeds to the next one. And each of the neurons learns like a weight or a set of weights that transforms their input. So um, you get this like, let me, each of these are neurons, right? And they all feed into one another, and you learn the weights between all the neurons, and that's what allows you to compute each of these uh, things. So you like put in some input over here, the input gets multiplied by these, then they get multiplied by these, and then they get multiplied by these, and then they come out the other side. And the entire process of training a neural net is learning the exact weights for these to get the desired output. Um, a convolutional neural net is a type of neural net mostly used in computer vision, uh, or not mostly, but it sort of originated in computer vision, where you have this input, right, an input image, say this like a human face, uh, right, and then we have a convolutional kernel that is of a certain size, right, uh, and then we convolve this kernel over the entire input. So every like X pixels, every N pixels, we move it to the right, and then we bring it down, right? And then we move it to the right again, and then we bring it down, and then we move it to the right again. So basically what we end up with is this output of, wait one sec. What we end up with is this output of uh, a lower dimensional representation, right, of this entire thing, where we only have the number of times we use the filter, right? So over here, we might have had like 100 pixels, but then since we only put the filter over it, like let's say 10 times, 100 divided by 10, we're only going to have 10 of those filter outputs over here. And then like same for the rows. Convolutional neural nets are especially good uh, because for a number of reasons. So the first reason is that you have a smaller number of weights to learn, right? So you only have to learn the weights of this kernel, right? This kernel that you slide over the entire input, and that's fewer weights than having to learn the entire an entire matrix for your entire input image, right? So it's better in that sense because there's less weights to learn. Also, you can parallelize the whole thing because you can perform uh, a convolution with one kernel over the entire image at the same time, right? Like it doesn't matter whether you perform the top left first or the bottom right first. You can perform every single convolution at the same time, which means that you can parallelize the entire operation. So each layer of this neural net is going to fire at once, or like in theory it can fire at once. So we have like a bunch of these convolutional kernels, right? They usually get smaller because we have like a smaller representation at each stage, um, and then they come out over here probably with just like if it's a binary classification problem, we eventually condense it down or use like a linear, like a normal neural net layer, right? A fully connected layer to output just like a single output, which can be like a yes versus no, right? Like 1 versus 0. Um, and then a 3D convolutional neural net is the same idea, except we perform it over 3 dimensions, right? Like you have a cube of input. That is a terrible cube. But you have a cube of input and you have a cuboid kernel, right? And you convolve over it in all 3 directions. So that's what a 3D convolutional neural net. And then a densely connected, this just means that every neuron is connected to every other neuron. Usually that's what it means, but that is almost certainly not what it means in this case. Like it doesn't mean that we have it doesn't mean that we have one huge okay, you can just we'll see exactly what they mean by this. Usually it just means that every neuron is connected to every other neuron, or um, they have a they have at least they have at least a few linear layers where every neuron is connected to every other neuron, right? So a linear layer is going to be such that you connect every one of these neurons to every other neuron in the next layer. But a convolutional layer isn't going to be like that, right? Because you have one kernel, um, and it outputs a bunch of different outputs depending on which part of the image you run that kernel on. So it's a slightly different idea, but we'll see exactly what they mean by this. Does anyone have any questions about this title? I think we sort of covered all the confusing buzzwords in this. Okay. Okay, cool. Did I lose you guys on neural nets? Is everyone familiar with neural nets here?
I mean, I've seen that diagram before. I'm not 100% clear on how it actually computes things, but I get the basic idea that there's connected neurons.
Yeah, I mean, it's basically just a ton of linear algebra, right? Like performing matrix operations. You can think of each layer in a neural net, like each densely connected or linear layer in a neural net, of being like the dimensions of in on one axis and out on the other axis. So basically for every input, right? For every input, you learn a bunch of values to transform it to the output dimensionality. So you have this like vector, right, that comes in, and then you multiply it into your neural net matrix, and then out pops a matrix of a vector of some different dimensionality that you define as this output dimensionality. And the entire task of a neural net is to learn those weights that allow you to transform from one dimensionality to the next.
Got it.
Cool. Yeah, it'll probably make more sense after you take AM20 or like linear algebra or whatever. But even before that, I think it's a pretty kind of elegant idea that you can usually grasp. Yeah. Okay, so let's just glance over the abstract. Direct synthesis of speech from neural signals could provide a fast and natural way of communication to people with neurological diseases, or just like telepathy, right? Like that would be cool. Invasively measured brain activity, ECoG, supplies the necessary temporal and spatial resolution to decode fast and complex processes such as speech production. Basically, they're just saying if we use EEG, right, like non-invasively, we're not going to get anywhere near the resolution, right? Like the data quality just isn't there from those high level like frequency spectrum bands. The data just isn't there when we're using EEG. But when we use ECoG, right, and we look at the cortex of a human brain, we're able to decode these processes such as speech production. Right, so people don't really understand how they've been able to decode these neural signals. Simple linear models, right? So that would just be like a linear regression where you just like multiply, like you here you have some input, right? And you learn a line to correlate this input to this output. This is just like on one dimension, right? But you can do this across higher dimensions as well. But they're basically just saying that there are almost certainly non-linearities involved in the brain that make it that will make it hard to just use a linear model to capture the relationship. It's going to be you'll probably like they're saying that you have to use a neural net, right, which has these inbuilt non-linearities in order to convert from neural activity to continuous spoken speech. Here they show that deep neural nets can map ECoG from speech production areas in the brain into a representation of speech. And they use this spectrogram, a log mill spectrogram, which is basically like they have a diagram of it somewhere down here. Not that. Here, this is like what a log mill spectrogram looks like, right? And then we can actually convert this into a like I don't think they do that in this paper, but there's a way for them to convert. There's a way for you to convert from a spectrogram like this into an audible format, like this speech waveform. So that's what they learn to output. And the proposed method uses a densely connected convolutional neural net topology, right? That just means the type of neural net they use. And it's well suited to work with the small amounts of data, right? Because you aren't going to be scraping like tons of data from the internet for this task. You actually have to go into the lab and install these ECoGs into people's brains. So there isn't like boatloads of data for you to train on. And they achieve correlations of up to 0.69 between the reconstructed and original log mill spectrograms. I don't think this is like an accuracy, this is like a correlation, right? So we'll see exactly what this number can be, like what the intuition behind this number is and like how good it is later on. But basically they're able to say that we're able to learn some kind of effective mapping that has a pretty high accuracy compared to the original spectrogram. Oh yeah, and then they do transfer their prediction back into an audible waveform. Yeah, it would be cool to hear those actual waves, but I'm not sure that they provide them. Supplementary content online. I wonder if they have like recordings. Nah, this is just or at least I think it is. Yeah, I don't think they published like recordings or anything. That would be cool. Yeah, and then this is the first time that high quality speech has been reconstructed from neural recordings. So that's why this is sort of a watershed paper, I guess, because this is like literally the first time anyone has done something like this. Right here, they're just talking about the research background. We can come back to this, right? They talk about some other papers that have done similar things. Yeah, initial studies have successfully applied deep learning methods to brain data, right? So people are starting to use neural nets for neuroscience, which is a relatively new thing. Before like 3 or 4 years ago, before EEGNet especially, most EEG analysis, and still like even now, like a decent amount of EEG analysis just happens in like MATLAB with linear models or like classical approaches like what's it called? Fourier transforms, independent component analysis, stuff like that. So using neural nets for brain signal analysis is still pretty new. Yeah. So here they say recent BCI studies are using the neural nets on raw signals rather than like crafting features or like having to do much cleaning beforehand. But they say that oh yeah, when we train on raw signals, it requires a lot of data to optimize, right? Because the raw signals are going to be a lot more dirty, right? They're not going to be as clean as just like handcrafted features. So in order to keep the parameters small, they use specific handcrafted features to extract information in the high gamma band. So we'll see exactly what that means, but they're basically saying that they have a layer of pre-processing before feeding it into the neural net. So and that's sort of different for them than other people, because for them they don't have enough data to be able to effectively learn, to be able to effectively train on such a small data set. No, sorry, they don't have enough data to optimally train a neural net if it were to just train on raw signals. So that's why they're using these handcrafted features. Yeah, for the transformations into a textual representation. I wonder what that is. That's interesting. But yeah, the resulting audio is of high quality and reconstructed words are often intelligible. So yeah, that's cool to hear. 6 native English speaking participants, right, while they underwent awake craniotomies for brain tumor resection. So that's kind of crazy. I wonder if they were compensated or anything, because that seems like they went in for a brain tumor and they just like ran an experiment on them. Interesting. Okay, cool. So here they describe like what their exact hardware is like. They placed it over the ventral motor cortex. So I think that's sort of isn't that like underneath? Wait, usually the ventral, my anatomy terms are pretty bad, but the motor cortex is like dorsal and ventral. Wait, is ventral like underneath? I'm pretty sure like, okay, wait. So
Ventral is up top, right?
yeah, dorsal is up top, right? Wouldn't ventral be like underneath the brain, like a ventral motor cortex? Or is it to the side? Is that what they're trying to show?
I think ventral is the opposite of dorsal.
So that would be like underneath the brain, which I don't think even has cortex. I mean, I'm not sure. I wonder where this is. But the premotor cortex is somewhere up here, right? Like the motor cortex is all in the parietal lobe. So that's like this region in the back from what I remember. So yeah, I guess all in this, like somewhere in this area, that's where they're actually placing these ECoGs. Grid locations were determined using anatomical landmarks and direct cortical stimulation to confirm coverage of speech articulatory sites. Oh, so that's interesting. So they somehow stimulated the participants to determine whether that's like the right spot. That's kind of interesting. I wonder if like that's applicable for like calibration for other neurosignal recordings. Like I wonder how you'd apply that to something like our project right now, stimulating maybe vocal muscles to determine whether we're placing the EMG electrodes properly. But yeah, that's something cool to read into. Participants were asked to read aloud single words shown to them on the screen while we recorded ECoG signals. Wait, what? So they went in for brain surgery. Their head is like literally open, and they asked the participants to read aloud words on a screen. I have no idea how they did that, because I would assume the person is under anesthesia.
Well, I mean, I don't know a whole lot about this, but isn't that a thing they do often during brain surgery? They give you like little diagnosis, like they give you little tests to
Oh,
make sure that they
really?
didn't accidentally interfere with
Oh,
you know.
yeah, I've definitely seen like movies or something where they do something like that, like to check that your brain is still functioning right. Yeah. Okay, that makes sense. Um, so the words were predominantly monosyllabic and consonant vowel consonants, right? So pave, dog, um, hit, stuff like that. Um, and they read between 244 and 372 words. Um, and total on average like 10 minutes per participant. Cool. Acoustic speech was recorded using just like a microphone. Okay. And they used this BCI 2000 software for like the data collection and like presentation. In terms of their data processing, right, this is the thing we talked about earlier. They had some like handcrafted features. So yeah, we calculated logarithmic power in the broadband gamma frequency. So ensemble spiking, that's what it correlates with. Yeah, so basically they compute the power of this gamma band after wait. Yeah, okay, yeah, something like that. So they run some kind of filter first and then they compute the power of the gamma band. What did I say here? Normalized. Interesting. Oh, so they actually like bucketed 200 milliseconds together of every point. So they actually it's not like every single second, like every single point in the recording is just from that point every single point in the data is not just from that point in the recording. Um, when they process this data, they're actually taking into account some context around each point. So they have like this 200 milliseconds of context. So now they have a feature shape of 64 electrodes, right? Those ECoG electrodes times 9 temporal offsets. So they only have like a 64 by 9 matrix. So I think they like bucket this into 9 times 200, right? So that's like 1800 milliseconds, which is about 2 seconds. So I think they're basically saying that the participants' recordings were like 1.8 seconds long, something like that. And then they bucketed it into these 9 temporal buckets along the time axis, where they just added up the broadband gamma frequency power, and then they reshaped this as an 8 by 8 by 9. I'm not sure why they just like wanted to use a 3D convolutional neural net, I guess. Yeah, I'm not sure why they had to reshape this as an 8 by 8 by 9. It is probably because when you have a 3D convolution, you're able to take more data for each kernel operation, right? You're able to take it from across all 3 axes rather than just along 2. So maybe by making it an 8 by 8 by 9, they are able to. Oh, you know what? No, actually, the reason they make it an 8 by 8 by 9 is because this is a square electrode, right? So this is a square electrode. So when they first get the output, right, this is like this is probably like an 8 by 8. But when they take the output of this, it's going to be a 64. So basically they just reshape it back into an 8 by 8 because that's what it actually was, right? So you have 8 along like the width, 8 along the height, and then you have this third dimension of 9, which is like temporal. And this would originally have been like 1800 milliseconds, right? But then they condense it down into these 9 buckets. So yeah, that's like how they structure this. So now they have this 8 by 8 by 9 input, right? That we're going to feed into our neural net. But here they also talk about processing the speech signal. So they downsample it to 16 kilohertz from whatever the mic's recording frequency is. uh, sorry, my throat always gets really dry halfway through these meetings. Uh, yeah, I mean they basically convert the audio recording into some kind of into this like log mel spectrogram. Cool. Any questions up to this point about this data processing or like the recording process or anything like that? Cool. Okay, I think we're about to get into like the interesting part, and then there's just yeah. So let's go through this now. To transform the recorded neural signals into that audio waveform, right? They trained densely connected convolutional neural nets to map the spatiotemporal broadband gamma activity onto a logarithmic Mel scaled spectrogram. So basically, they're just converting from this 8x8x9 into this log mel representation. And they're training a convolutional neural net to do that. Once they train that model and it outputs a spectrogram, they use a WaveNet vocoder to convert from the spectrogram out to a to an audio format. This is not like not part of their research, I guess, right? Like this is a like WaveNet already exists and is already used all the time for converting from spectrograms into an audio waveform. So they're just like sticking that onto their components so they can like test more easily to see like, is this spectrogram that our neural net is outputting, is it actually audible and does it make sense? So yeah, so here's a nice diagram of the entire thing. So we have all this activity, right, on this like square over here. We bucket it into these nine time-based windows, right? And then we have like 64 along this axis, right? 64, 64, 64. And then they convert it into an 8x8x9 by 9, right? And then they feed it into this 3D convolutional neural net, which has one convolution operation, then a dense block, which means a like linear connected layer, right? Like I was showing earlier, where every neuron is connected to every neuron in the next layer. Then they have another convolutional operation. Then they have a pooling layer. I'm not sure what these are, but then they have another dense block, another convolution, and then a final linear layer. Not sure what they mean by dense block then. Maybe it's just a bunch of linear layers stuck together. That's usually what it means. We can look up DenseNet real quick and just see what the architecture is. Connects each layer to every other layer in feed-forward fashion. Whereas traditional convolutional neural nets with, okay. Oh, so this is the same idea as what's it called? There are other papers before this that do the exact same thing. What is it called? Okay, this is not the first time I've seen this. Okay, I can't, it's like skip forward connections or something like that. Or like hopping connect. Does anyone remember what those are called? I'm not a computer vision guy, but this was like from 2014, where they have, it's exactly this diagram where you have, for each layer, it outputs to every other layer in front of it. It's called like skip connections or something like that. Something like this. Is that what this is? Here, let's check this. Right. So it's sort of a similar idea. You skip some layers. So you like forward, yeah, residual connections. Yes, ResNet. Of course, that's what I was thinking about. Yeah. Yeah, this is what I was thinking about. We can like look at, maybe there's, yeah, so with a ResNet, right, you have these residual connections where you feed forward, right, directly, but you also skip a few layers and feed all the way to the end. With DenseNet, I think the idea is that you feed, wait, what? Okay, my understanding of DenseNet based on what this paper just said is that you would feed this layer forward and then also forward to the end. Maybe that's what this diagram is showing. But I'm not sure. Anyway, I think, yeah, because then if you look at this DenseNet kind of thing, right, that is what it shows over here. Maybe DenseNet is about adding the features from one layer to the features of the next, right? This addition operation rather than just like replacing them. But then that's what they show ResNet doing over here. But I mean, it's probably best to look at the paper. So if you guys are interested in this exact kind of architecture, you can look into that. But basically they have a convolutional neural net with these dense connections. And then, so yeah, out of this convolutional layer, right, we go through the linear layer and then we output this log-mel spectrogram, right? So we get this big matrix at the end that has like it's like a heat map, right, of the activations for this spectrogram. And then we output this to the vocoder that's going to convert it to an audible waveform. Does this diagram make sense to everyone? This is sort of the core, like this basically summarizes the paper. Okay. Oh yeah, and here they have a, okay, I mean, they talk about it here, but yeah, okay, they don't talk about DenseNet specifically. Oh no, they do. Okay, so, oh yeah, okay, wait, so they literally talk about this. Okay. Yeah. All right, so yeah. Yeah, I mean, we I guess we just sort of talked about all of this. We didn't have to look all of this up. It seems like they were just about to talk about this on their own. Lol. I don't think, just checking if there's anything that we didn't cover that is here. Yeah, so they use 3D convolutions and 3D pooling layers, right? Because they have the X, Y, yeah, so that was right what I said earlier, right? They have the X and Y position within the electrode grid, and then the 9 dimensions for time. Sorry, 9, or actually, yeah, I mean, nine dimensions for time. Like there are 3 axes, right? And each of those axes has these dimensions in it. So you have an 8 by 8 by 9. Right, and then they have their convolutional kernel is a 3 by 3 by 3. Yeah, they have 83,000 trainable parameters, right? So it's not huge. It's like big, of course, but it's not like huge. And then they use Atom for training. That's pretty standard. 80 epochs, also pretty standard kind of thing for this task, I would expect. Oh yeah, and then here they talk about the WaveNet vocoder architecture. I don't think this is too important, right? Like we can always look at the actual WaveNet paper if we want to cover this, but basically, yeah, I'm not sure. So I think the idea is that you record a waveform for a person, and then you also record a spectral, like the spectral features. This is completely separate from the neurals, like the brain recording stuff, by the way. This is how you would train the WaveNet vocoder separately, but there are already plenty of like pre-trained models of WaveNet that you could use. And I think they did state that they use a pre-trained model. So sounds like it's an autoencoder or something almost, where I mean, I'm not sure why they're inputting this waveform over here. That's the main thing that confuses me here. Yeah, I mean, I guess the main thing you need to know here is just that we're trying to map this spectrogram to a audible waveform. Right, so they use wavenet conditioned on acoustic features estimated from Mel-Sepstrom vocoder. So I guess there are wavenet, like specific wavenet models that have been trained for this log Mel spectrogram. So that's the type of vocoder they use. Tacotron, right? Chris probably sort of remembers this from our work last summer because one of the interns there was working on like Tacotron for text to speech analysis. But yeah, so talk about the internal architecture. This stuff isn't too important, I think, right? Yeah, none of this is like core to the paper here. Oh, so they do actually train it though on their own, or maybe they like fine tune their wavenet vocoder. Cool. Okay, results. So for each participant, we partition the recorded data into disjoint sets for training and testing, 5-fold cross-validation, right? So I think cross-validation here especially is pretty important because they don't have that big of a data set. So in cross-validation, we we hold out one. So the problem that cross-validation tries to solve is that you might get a really lucky split of your data, right? If you randomly split your train and test, you might get a train set that is like virtually identical to your test set just by like chance, which results in like abnormally high accuracies. So what we usually do is like a n-fold cross-validation where you take a bunch of random splits of your data, right? Like 5 random splits, and then you hold one out at a time and use that random 5th fold to validate on. So that just ensures that we aren't getting lucky on our split and we're not operating on data that has been seen before. And then they hold out another 20% of the data for some reason. Right, so then they use the Pearson product moment correlation for evaluation, right? So they were saying earlier, right, they have a 0.67 correlation between their output signal and the actual, like, what's it called? The actual audio signal. So they correlate, they compute that correlation using this. I've seen this in a few other papers now. I should really like look into what this exact statistic is. Like the Pearson correlation. We've definitely seen that before, yeah. It's probably some elementary kind of stats ML idea. Like that's another thing, guys. Like my elementary stats knowledge is very lacking. Like I regularly find holes in my like basic stats knowledge of just like things that should be basic stat stuff. So sort of just suggestion, like ML is good, but probably don't dive, or I mean like totally feel free to dive like straight into neural nets if you find them interesting, but then like at some point it's pretty important to like go back and brush up on stats stuff. Like that's like sort of what I'm in the process of right now. Just like learning some elementary stats ideas. Because it's pretty important. Like you have to have intuition for those before you can really understand how like neural nets operate. Right, we achieve correlation significantly better than chance level, right, for all 6 participants. So for one of the participants, they get 0.19. Oh, wow. So for some of them, they're like, it varies a lot by participant. So this one participant has 0.69, which is like way better than all the others. This might be due to having electrodes placed in a better position. So yeah, that's another thing with neurosignals always, right? Like there's like a huge component of it is placement of your electrodes, and even placing your electrodes slightly differently could completely change your outputs. And even when you average across all the participants, it's still considerably above chance levels. Okay, cool. Thanks, Cameron. So yeah, in order to evaluate the intelligibility, they employ the short time objective intelligibility measure. So they actually, I thought they just like did this by ear, right? They just listened to them both and then guessed whether they would be intelligible. But it seems like they have a formal mechanism for determining that. Cool. Reconstruction performance of DenseNet compared to random chance, right? So for all the participants, especially like participant 5, right, who way overperformed, it's way better than chance level. And then the logmel bins, right, the DenseNet does really well. And then this is the STOI that we were just talking about, an objective intelligibility measure in comparison to chance, right? So this isn't nearly as much better than the Pearson correlation they have, but it's still clearly better, right? For participant 2, though, you can see how it's like pretty bad for like the way they measure STOI. So this is another thing you could look into, STOI scores and like how they work. Maybe they talk about that here. No, I don't think they do. But yeah, cool. So they just like sample one to show over here, but just like visual inspection, right? These look pretty similar, vaguely. So I think B shows a generated waveform. Spoken words are given below. So the actual one is over here, and then this is like the prediction. So I mean, it does a good job of like at least segmenting the words, right? Like it's pretty good at recognizing like where a word it starts and stops. But the actual waveform of the word, it varies a lot, right? Like some of these are pretty good. I don't know. This one, these match up quite a lot. But then other ones are like, what was it thinking? Or actually over here, it's just an amplitude thing, right? If you just like up the amplitude on this one, they look pretty similar. So yeah, I think yeah, it's pretty good. Also, just like a cool phonology linguistics thing, you can sort of see the spectrogram, right, for space and spear. You can see how like the S, there, like it starts over here, and then you have like the rest of the, there's like a small space. There is a small space in space, yes. There is a small space between the onset of the S and like the rest of the word. Kind of interesting. Cool. So that's about it, right? They have shown that they can do this pretty effectively up to R 0.69, up to R of 0.69, of converting from just these brain signals into a audible format. This is the first time it's been done. Especially impressive. Yeah, I would totally agree with this, right? Like they only have 12 minutes of data or something, or 12 times 6 minutes of data. So it's like pretty great results for such little data, because usually with these huge neural nets you need tons of data to train them. So yeah. Yeah, future areas of research might be like in paralyzed patients, right? That might be interesting. And probably the biggest kind of problem to improve is implementing it in real time, right? Because right now I think for them, they're like the time bucketing is probably not as feasible in real time. But I think, I'm not sure why they're talking about this. I think the biggest issue for them is probably the placement and just like how much the accuracies vary over participant. That would be like my biggest concern. And that's what we're working on in our project as well, right? Like when you have one participant in your training data, we get something like 0.93 accuracy. but as soon as you add another and you add like 2 or 3 more, the accuracy drops down a lot. So with neurosignals and like biosignals in general, I guess like one of the biggest problems is always calibration. So yeah, I think more researchers need to understand speech representations in paralyzed patients. Yep. Great. Great. Cool. So yeah, that's about it for this paper, guys. Do you guys have any questions? Anything we should go over again?
I had a question about the architecture of the model. I
Mhm.
think next page.
I think it is this one, right? Oh, or vocoder. You mean the vocoder?
Yeah. So I don't have too much experience with like non CV CNNs, but that last function, like MOL,
Mm-hmm.
what is that? I've never
I have no idea what that is. Mixture of logistic distributions. Yeah, I've never heard of that before. Let's check it out. Yeah, so it's like a pretty, I mean, it's a type of output function, right? Oh, it's an alternative to softmax. So
Okay.
yeah, it's sort of like softmax. I guess the blue over here is what, or no, I don't think. I mean, let's just open this. Yeah, I mean, I guess it's just an output to softmax. So basically, when you have a bunch of outputs, right, and you want to convert it from some discrete probabilities to a curve or a function that you can sample from, that's what you use softmax for. So like it's the same kind of idea. Speech synthesis, right? So it's almost all like it's pretty specific to
speech.
yeah. I don't think it's I would be surprised if it were inherently better than softmax for speech recognition. I guess it for some reason just became like the standard in this specific area of research rather than softmax.
Yeah, because like in most CV papers, you see softmax like
Yeah.
making rectified linear all the time.
Yeah. So I think it's just like a quirk of like speech synthesis research that they use this instead of softmax. But yeah, you can see softmax is just like infinitely more popular. And MOL is like down here.
That just that's all papers.
Yeah. But it's actually cool. I didn't know papers with code had like features like this. That's super interesting. Yeah. Cool. Okay. Yeah. Any other questions? Okay. I think that's about it then for today, guys. Yeah. Thank you.